section, which is going to be a quick review of math and chemistry. And the reason I do this is just to make sure everybody has a clear understanding. We are going to do work on problems, calculations, and so on. I want to make sure you have a basic understanding of math. A lot of times I've had students tell me they had to have math for 20 years and can't remember how to do some of the stuff. So this is a way to just make sure we're all up to speed. I'm going to make the assumption everybody knows how to add and subtract, multiply, and divide. When we work with fractions, which we will do in this course, certain things we do about if we want to add fractions. For example, here we got 1/2, 1/4, and 1/3. We want to add those up. What we do, we find a common denominator for those. In this case, it's 12. And so we multiply each one of those fractions by unity. In this case, 6/6, which is 1. We haven't changed the number at all. We get 6/12. 1/4 becomes 3/12 and 4/12. We add those up. We add the numerators. We get 13/12. And if we did the division of 12 into 13, we'd come up with 1.08. And so the addition of 1/2, 1/4, and 1/3 would equate to 1.08. Another way to do that is convert the fraction into a decimal form of the equation, in which case we would have 0.5, 0.25, and 0.33. If we add those up, you'll find that likewise equates to 1.08. When we multiply fractions, what we do is we multiply the numerator times the numerators and the denominators. In this case, example here, 1/2 times 1/3, we would get 1/6. Again, dividing 1 by 6, we would get 0.16. Or we could do it from the decimals standpoint, 0.5 times 0.33. Did that multiplication, you would come up with 0.16. When we divide fractions, for example, 1/3 divided by 1/2, what we do is we invert and multiply. So we got 1/3 times 2/1, which would equate to 2/3. And again, do that division, and we get 0.66. Or we could do it in a decimal form, much like we've done the others, and that would come out as 0.66 as well. I want to talk a little bit about exponents and some of the basic laws of exponents. We can refer to exponents or express exponents by b to the nth, which would equate to b times b times b, however many times we want to multiply that number. And we can express that as b to the nth power, where b is the base and n is the exponent. And it's given some certain rules. B to the 0 power equals 1 if b does not equal 0. And b to the nth time means we're multiplying the base times that many times. So if we got b squared, it's b times b. In this case, we got 2 cubed. It would simply be expressed as 2 times 2 times 2, which would take 8. Some of the other laws of exponents is b to the minus 1 can also be written as a fraction form of 1 divided by b to the nth. Example, 2 to the minus 3 would be 1 divided by 2 cubed, which would be 1/8. We could do b to the n divided by m, so we've got an exponent in a fraction form. We can express that fractional exponent as n, the square root of b to the nth power, or we could take the nth root of b to the nth power. If we're multiplying exponents with the same base, we can simply express it as b to the n plus n. If we're dividing the same base by various exponents, we can express it as b to the n minus n. And if we're multiplying for taking a base to the nth power to the nth power. We can express that by multiplying the two exponents together. If we have two bases, a and b, and we've expressed it as to the nth exponent, we can also write that as a to the n, b to the n. Again, a fractional of the multiple bases can be expressed as a to the n over b to the n. Another types of scientific notation that's commonly used in industrial hygiene is logarithms. And basically, when we're dealing with logarithms, it's just a means to be able to express big numbers into smaller numbers. And we do that by primarily focusing on the power of 10 and utilizing numbers between 1 and 10. So now in this particular course, you won't be asked to do any calculations utilizing logarithms. In the advanced course, you do. Another way to express a logarithmic function, we see a to the x power equals y. That calculation can be expressed as x equals the log a of y. Now, we use scientific notation primarily to help us deal with big numbers or make dealing with big numbers easy. For example, we can take 253, we can condense that number down to 2.53 times 10 to the 2 power, or 10 squared. Or we can take 0.0253 and make it 2.53. And we do that by taking it to the 100th of that and express it as 2.53 times 10 to the minus 2. So to show how it makes it easy to use scientific notation to make big numbers easy to work with. You know, if we had a number like 378 billion times 0.000004 divided by 2,000, you know, if you tried to start plugging those into your calculators, if you didn't have a scientific notation calculator, you would probably come up with some kind of an error. But what we can do is to make it easy to work on those numbers is use scientific notation. We can express 378 billion as 3.78 times 10 to the 11th power. And this 0.000004 we can express as 4 times 10 to the minus 6, and divide it by 2 times 10 cubed. Now we've got numbers that are easy to work with, and we can rearrange those numbers. 3.78 times 4 divided by 2 times 10 to the 11th minus 6 minus 3 power. Do that math, and we come up with 7.56 to the 10 squared power, or 756. So you can see that's what scientific notation is used for. In our course, you will see both metric and English units used, but we utilize probably more metric units in industrial hygiene than we do English units. So we need to all understand, when we talk about micro, what that means. Micro refers to 1/1,000,000th of a number. Milli refers to 1,000th of a number. Centi refers to 100. And kilo or kilo refers to 1,000th of the number. 1,000 of the number. So if you have a microliter, you're dealing with 1/1,000,000th of a liter. If you have a kilometer, it's 1,000 meters. Looking at units of length, we have one meter equates to the English unit of 3.28 feet, or 39.97 inches. 1 micrometer, which is also referred to as a micron, refers to 0.00003937 inches. 1 millimeter with 0.03937 inches, and 1 centimeter would be 0.3937. For units of volume, 1 liter is the same as 1,000 cubic centimeters, and 1 cubic centimeters equals 1 liter, 1 milliliter, which equates to 0.038 fluid ounces. 1,000 liters equates to 1 cubic meter. So it's important to know that to be able to do some of our calculations. For units of mass, we have 1 gram equates to 1/1000th of weight of 1 liter of water. So 1 microgram would be 1/millionth of a gram. 1 milligram would be 1/1000th of a gram. And 1 kilogram would be 10,000 grams. Okay, looking at a quick review of chemistry. There's basically, we need to remember there's 3 states of matter: solid, liquids, and gases. Liquids are formless fluids which takes the shape of its container. Take any liquid, put it in a container, and that liquid is going to take that shape. A solid is a substance that has a definite shape and volume. It's going to be a fixed shape and volume. And gases are going to be formless fluids which uniformly distributes itself throughout its container. Gases have low density and viscosity. A gas, for example, the air in this room is composed of gases: oxygen, nitrogen, and some other gases. These gases evenly distribute itself throughout this room. There's the same amount of oxygen and nitrogen at the back of the room as there is up here at the front of the room. Well, chemistry is basically the branch of science which plays a role in us being able to characterize and quantify toxic substances. Now, we have 2 general branches of chemistry. From your early days in undergraduate work, you may recall organic and inorganic chemistry. And when we look at the simplest form of a chemical, it's referred to as an element, and it's basically made up of atoms. If you had a periodic table, you would see those elements listed on that table: oxygen, nitrogen, hydrogen, and so on. And each of those elements are made up of atoms. And if we look at the atoms, they basically are composed of protons, neutrons, and electrons. And this is an atom of beryllium, for an example. You can see here the protons are in the center of the nucleus. For beryllium, that's 4. And it's a positive charge, the protons are. And then around the orbital of that nucleus, we have electrons. And those are represented by these red dots. They are a negative charged particle. So for an atom to be in balance, you're going to have the same number of protons as you are electrons. So that way it will be electrically neutral. We also have in the nucleus what is referred to as neutrons. They don't have a charge. They're basically neutral. Now, each one of the elements is going to have equal protons and electrons. Now, each element has a name, and associated with it is an atomic weight. The atomic weight of the element is basically the number of the protons and neutrons of that atom. Now, compounds are basically composed of 2 or more elements which combine. The smallest unit of a compound is going to be referred to as a molecule. Some examples of that would be sodium chloride. We've got a sodium chloride element. Or another common example is H2O, 2 hydrogens and 1 oxygen. Now we can have a molecular weight of a compound. So if we want to know what the molecular weight of sodium chloride is, what we do is we take the atomic weight of sodium and add it to the atomic weight of chlorine, and we would get the atomic weight for sodium chloride. Same with water. We took the weight of water, atomic weight of water, or hydrogen, I'm sorry, and the atomic weight of oxygen, and we come up with the molecular weight of that compound. When we deal with inorganic chemistry, we can define it as basically non-carbon containing compounds, elements or compounds, or carbon compounds which contain a mineral or non-organic quality. For example, examples of non-carbon containing would be mercury, lead. Examples of compounds that are carbon-based but do not have minerals or non-organic qualities: carbon monoxide and carbon dioxide. From an industrial hygiene standpoint, in industry, some of the common inorganic hazards that we encounter are going to be like in the form of dust, such as silica, SiO2, asbestos, other mineral dusts. We can have gases and fumes such as nitrous oxides, carbon monoxide, ozone. We can have acids, such as hydrochloric acid, sulfuric acid, and alkaline materials, or bases, sometimes referred to. Examples be sodium hydroxide and potassium hydroxide. More commonly, the industrial hygienist deals with carbon-containing elements or organic chemistry types of compounds, elements and compounds. And basically, when we're dealing with organic chemistry, we're dealing with carbon elements which characteristically are similar to living tissue. And again, the exceptions are going to be those inorganic substances with carbon, such as carbon monoxide, carbon dioxide, carbonates, and carbonyls. Some of the common elements found in organic chemicals, the most common found are carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, chlorine, bromine, and iodine. If we look at the basic building block then for organic chemicals, we start off with the carbon atom. And as we know from our chemistry days, the carbon atom has 4 covalent bond locations. So you can bond a chemical. There should be a little line up here, and a line down below. And so you got 4 bond locations, 1, 2, 3, 4. And you can bond other elements to any one of those covalent bonding locations. Now, when we have a carbon element and it has individual bonded other elements associated with it, then we refer to that as being a saturated carbon. Saturated means we've got 4 bond locations taking place on that carbon. When we talk unsaturated, it's when we have 2 or more carbon elements sharing the bonds. So in this first example here, you can see we have 2 carbons sharing a double bond. In the second example over here, we have 2 carbons sharing 3 bonds. There's more than 1 million organic compounds. When we deal with carbon and hydrogen compounds, they are going to be referred to as hydrocarbons. And there's various forms of hydrocarbons. We've got aliphatic hydrocarbons. In a saturated hydrocarbon, it's going to be referred to as alkanes, A-N-E-S, in the ending. That tells us that that chemical is going to have a single bond. So if we see something with the name trichloroethane, we know we're going to have multiple carbons with a single bond because of the A-N-E. Some other examples of alkanes are methane, ethane, propane, butane, hexane, etc. For unsaturated, if we have double bonds, they're going to be referred to as alkenes, the E-N-E-S. Example is ethene. Or triple bonds are going to be alkynes. Or in this case, a example would be acetylene, where we have a triple bond. The more bonds you have, the more active the chemical is. It wants to get back to a single bond state. So when we look at reactive chemicals, we're going to see this triple bond, it wants to break apart. So it's going to break apart easily when it is given the right conditions to cause the breaking of that triple bond. So we had aliphatic hydrocarbons. We also have aromatic hydrocarbons. And for aromatic hydrocarbons, what we do is we start out with benzene. And we've got the benzene ring. Now, benzene calculation or a formula is 6 carbons and 6 hydrogens. So at each one of these points, we would have a carbon. And to that carbon, again, we would have 3 other bonds available to bond with. And so we can bond a number of different compounds or substances, elements, at each of those carbon bonding locations. Now, if we took, for example, here, if this is going to be right or not, we'll try. If we say bonded here, right, at this location, if we put a methane bond, put a methane bond at a location like this, then we would form a chemical that would be called toluene. And if we put another methane group at another point on this particular ring, we would call it toluene, or xylene, I'm sorry. And so we could bond, note on here, so if we put a methane group here, that would be toluene. At this bond location, we could also put a methane group, and this would be xylene. Now, for the second methane group, we could put it here, or here, or here. And when you see a chemical, when you see xylene, you'll see a reference to ortho, meta, and para. And what it's telling you is what is the bond location of that second methane group. So you can see we've got a lot of flexibility, and those would be isomers of that chemical. Okay, now we can have halogenated hydrocarbons. When we have halogenated hydrocarbons, what we're referring to is putting either a chlorine, bromine, or iodine, are the most common ones, in the chemical structure. For chlorinated hydrocarbons, aliphatic chlorinated hydrocarbon, we would have something like carbon tetrachloride, CCl4, or trichloroethylene, or trichloroethane, which are examples of these compounds. We can also have aromatic chlorinated hydrocarbons. We would start off with the benzene ring, and for chlorinated aromatic hydrocarbons, we'll often see the name phenol written here. So anytime you see that name, you know that there's a benzene ring involved. A good example of that would be polychlorinated biphenyls. We know that we're dealing with benzene aromatic hydrocarbons. Alcohols, what we will see is a base, R being something, maybe a methane group or ethane group, whatever we want. And to that, we bond a alcohol group or an OH group. The easiest or basic example of an alcohol is methyl alcohol. And all we do is we bond a methyl, we take a methyl compound and bond to an OH. Another example would be ethyl alcohol, and what we do would have 2 methyl groups and bond an OH material or compound to it. For ethers, you have 2 base roots of the same type, and in between them you'll have an oxygen bond. And here's a basic example of the ether. We got methyl, ethyl, ether. So we got a methyl group, an oxygen, and then an ethyl group. For aldehydes, when we talk about aldehydes, we're going to have an H or base root and a carbon double bonded oxygen to it. If we took our basic aldehyde, we would have our hydrogen group. We would put another hydrogen group to that carbon, and the oxygen molecule we would have formaldehyde. For ketones, we'll have the base group with a carbon double bonded oxygen and another base group. Example here is methyl ethyl ketone. And we've got methyl group, ethyl group bonded to our ketone molecule, which is a carbon double bonded oxygen. Oftentimes you hear reference to solvents. When we talk about an aqueous solvents, they're basically going to be a water-based solvents. These are going to be things like your acids, alkalins, detergents, and so on. They'll typically have low vapor pressure, so they're low vapor hazard. Organic solvents are made of organic chemicals. They're used widely and present an inhalation and skin contact hazard. We talked about forms of matter. In industrial hygiene, we can expand on those a little bit. We have chemical states of matter are going to be primarily our liquid, solid, and gases. Again, a liquid is a formless fluid which takes the shape of its container. A solid is a substance that has a definite shape and volume. Example, like this book. Gases are going to be formless fluids which uniformly distribute itself throughout the container that it's in. In industrial hygiene, we expand on that a little bit. We talk about gases being formless fluids which uniformly distribute itself throughout its container. But we can also have vapors. Vapors are basically gaseous forms of a material which is normally a solid or liquid at room temperature and pressure. But you change the temperature or pressure, you can change that liquid or solid into a vapor. And you take away or change that temperature back, and that vapor will revert back to its liquid or solid state. Then we can have fumes. Fumes are basically solid particles formed from a volatile solid which condenses in air. Now, fume is one of the most misused terms that we have when in talking about chemical hazards. Even in the media, you could have a chlorine gas leak, and the media is going to say we've got toxic fumes. Well, it's not toxic fumes, it's toxic gases. Because fumes are a solid. They're a solid particle. The best way to visualize a fume is through a welding process. You take heat, high temperatures, apply it to a metal, and you'll see that solid metal melt. And if you look through a welder's hood, it would turn into a liquid on top. That liquid, as it continues to heat, will vaporize off. Now, once that vapor from that hot liquid reaches cool air, that vapor condenses or solidifies and forms that solid. Now, that solid is very small in diameter. Typically, when we're talking about fumes, we're talking about a particle size of about 1 micron or less. So fumes can easily get down into the deep regions of the respiratory tract system. Other chemical hazards from the industrial hygiene perspective are dusts. Dusts are a solid particle created by some mechanical actions such as grinding, crushing, pulverizing, etc. And most key to us in the industrial hygiene profession is the size of particles that can get into the body. Now, we refer to those size particles as respirable size. So if we say it's a respirable dust, it means it's a 10 microns or less in size. So respirable means it can get into the body, into the bronchial passageways, and potentially into the alveoli. Mist are suspended liquid droplets, which are generated from, again, some mechanical action that breaks down a liquid, such as spraying it or other types of processes that break that liquid down. Spray painting is an example of where we could generate a spray paint mist. So that's a quick review of our math and chemistry. You want to break now? Oh, okay. You don't need to break at 10:30? Okay. All right, then in that case, we'll continue on with our next section on anatomy and physiology. It's important for us to understand a little bit about the anatomy and physiology when we talk about health hazards, to have an understanding of what goes on inside the body that these chemicals can get in and cause damage to. And we'll start by reviewing of the respiratory tract system, or the lungs. When we deal with the respiratory tract system, this is one of the most quick and direct means for a toxic substance to get into the body, because what do all day long is we breathe. We have to breathe. And when we do that, anything that's present in the air is going to be drawn in to the body, including if toxic materials are present, they're going to be introduced into the body. Once they're introduced, they could do various degrees of hazard. When we talk about metabolism, what we're referring to is metabolism is the process where the body combines oxygen with food to produce energy. So each cell consumes oxygen, and when it does, it produces a byproduct. And when that byproduct comes in the form of carbon dioxide. So the lungs are the passageway for oxygen to get into our blood system, and it's also the passageway for those byproducts, such as carbon dioxide, to be eliminated from the body. If we actually looked at the anatomy of the lung, we can see it's the largest organ inside the body. It comprises about 300 square feet of surface area and as high as 1,000 square feet of surface area when we take a full inhalation. From an industrial hygiene standpoint, the lung is the primary importance because it's the largest source of exposure that we encounter is through inhalation. So the function of the lung, it's a mechanism for oxygen, primarily for oxygen and carbon dioxide to be exchanged. It also is a mechanism that allows oxygen and carbon dioxide the ability to mix in the blood. Taking a look of the respiratory tract system, we have the upper respiratory tract system, which is composed of the nose, which allows entry of air. In that nose area, we have mucus and cilia, which are little hair cells. They're part of the natural body defense. Then you've got the pharynx, which is down in this area, which goes on further down the esophagus down to the larynx area. Again, the larynx area has mucus and cilia to trap particles that might come into the respiratory system, and eventually down into the lower region of the upper respiratory tract, which is the trachea. And the trachea, it too, has the mucus and the cilia as natural body defenses. Then we get into the lower respiratory tract system, which is composed primarily of bronchial passageways. That's these large blue areas. And then down to the bronchi, bronchioles, which are the smaller thread-like. And then finally, all the way down to the alveoli, which are the air sac that you see in the lower, off of the bronchioles. They dead end into the alveoli. And the alveoli sacs are where the oxygen or gas exchange takes place. So if we look at the alveoli, the gas exchange takes place here. Now, around the alveoli sac, you'll have all sorts of capillaries. And that alveoli sac area is like a 1 to 2 cell membrane. And so it's real easy for the gases to transfer from that sac area into these capillaries and then be introduced into the blood system. That gas exchange takes place based on the pressure, the partial pressure of those gases. So if the partial pressure of oxygen is greater in the air sac, it's going to diffuse over into the capillary. And then once it's in there, it's going to be picked up in the blood system, carried throughout the body. Likewise, the carbon dioxide, the partial pressure of it in the blood gets high, then it diffuses that carbon dioxide gas into the alveoli sac area, which can then be exported out of the body through exhalation. And this whole mechanism is controlled by the brain. The medulla measures the carbon dioxide concentration and will correspond with the breathing rate to exchange that gas and bring in fresh oxygen. Typically, our respiration rate is 12 to 18 minutes or breaths per minute. That'll vary individual to individual. We take in approximately about 500 milliliters or cc's of breath. And during the course of the day, we take in about 4 million cc's or 4 cubic meters of air. In industrial hygiene, we also kind of have a region breakdown of the respiratory tract, and that is the nasopharyngeal region, which basically refers to the inhalable fraction of chemical compounds. And notice that it stops up around the beginning of the tracheal area. And so large particles will be filtered out and trapped in this nasopharyngeal area. Then the next lower region goes in the tracheobronchial region. It includes the trachea and the bronchi. And then we refer to that as the thoracic fraction of particles. And finally, we get in the deepest regions of the bronchial alveoli area, and that's our pulmonary region, and that's our respiratory fraction of compounds that can get down into those regions. Again, a little bit of anatomy of the respiratory tract system. The respiratory surface of the lungs, as I mentioned earlier, ranges from about 300 square feet to 1,000 at the deepest respiration. The alveoli sac is 1 to 2 cells thick. We breathe about 300 cubic feet or 8.5 cubic meters of air in an 8-hour day. We breathe approximately 4.3 to 5.7 liters per minute, or about 12,491 liters per day. Our total lung capacity is about 6 liters. When we inhale air, typically good air is going to contain 21% oxygen, approximately 78% nitrogen, and 1% inert gas. So every breath we take in those gases. When we exhale air, if we could look at the composition of that exhaled air, we would see that it would have about 16% oxygen. So you can see there, about 4 to 5% oxygen has been dumped off into the body. You'll have about 4% carbon dioxide and 80% nitrogen and inert gases. As I mentioned earlier, the air exchange takes place by the pressure differential and the gas diffusing across into the blood. This is just an example. Typically, our partial pressure of oxygen in there is 159 millimeters of mercury. This goes in, when it gets down into the alveoli sac area, it's down to about 110 millimeters of mercury. In the blood system, our partial pressure of oxygen can get as low as about 40 millimeters. When that happens, the pressure difference from 110 to 40 causes the oxygen to move over or diffuse into the capillaries in the blood system and eventually be carried around the body. Likewise, if we look at carbon dioxide, the partial pressure in the blood is around 46, in the lungs about 40, and outside is about 0.3. So again, we get diffusion of carbon dioxide from the blood into the alveoli and eventually out to the next alveoli. Now, the body has a number of natural body defenses. Those include the mucus lining and the cilia. Mucus lining traps it, and the cilia hair cells will move that mucus eventually upward and outward. Coughing and sneezing is a mechanism. Body defense. However, the respiratory tract doesn't have a good body defense for gases, because gases are molecular in size. They're so small, they can immediately, just like oxygen being a gas, go down into the alveoli sac area. Just like oxygen, the partial pressure of those gases are going to be higher in the alveoli, so those gases immediately diffuse into the blood system and be carried throughout the body. As we mentioned, when we have large particles, and we can define those as greater than 10 microns, they're going to get deposited in that upper respiratory tract system, the trunk, the nose, the throat area. The smaller particles, 10 microns and below, are going to get down into the bronchial regions, and the smallest particles, less than 5 microns, are actually going to get down into the alveoli air sacs. Now, once we get down in the lower regions of the respiratory tract, we have another body defense, which are white blood cells. And those white blood cells are basically garbage eaters, if you will. They're phagocytes, are the names of the cells. And what they do is they ingest particles or foreign substances and ingest them. And once they do that, those cells can embed themselves into the mucus lining and eventually be worked out of the body. So that's the body of defense for the respiratory tract system. Let's look a little bit about the anatomy of the skin. The skin has approximately 20 square feet or 2 square meters of surface area. And the thickness of the skin is going to vary between about a half a millimeter on the eyelids to about 3 to 4 millimeters on the palms of the hands, the soles of the feet. There's 3 basic layers of the skin. We got the epidermis, dermis, and the subcutaneous layer. And here we see a cross-sectional diagram of the various composition and that anatomical composition of the skin. You've got your upper layers, outer layers, stratum corneum up here. You have sweat ducts in here. That's a heat regulator. You got sebaceous glands, which keep the body and the skin oily, greasy. You have your sweat glands, again, a thermal regulator. Blood vessels that supply the dermis and epidermis areas. You got fatty tissues, hair follicles, and certainly capillaries throughout this area of the skin. If we kind of looked at a breakdown of the epidermis, dermis, and subcutaneous, the top outer layer is our epidermis area. And you can see illustrated on this side here. It's primarily serves as a barrier to foreign substances that are out in the environment. Those cells on the epidermis area will eventually die and be replaced, and they flake off. Millions of those cells do that daily. We have the dermis area, which again, it's now down into our deeper skin anatomy. Here we're going to find the sweat glands, the nerves, muscles, blood vessels, basically referred to as our factory area, if you will. And then finally we go down in the subcutaneous, where we get into it's the fatty layer between the dermis and the muscles and bones. There's a lot of nerve ending, a lot of blood supply that is provided through this subcutaneous layer into the skin. Well, like the lungs, the skin does have a natural body defenses. Intact skin has a number of natural defenses. Basically, the epidermis prevents absorption of chemicals and is also a physical barrier against biological hazards such as bacteria. We got the sebaceous glands, which secrete fatty acids, which are fight off bacteria and fungi. Then you've got the skin pigments and melanocytes that prevent damage from ultraviolet radiation from the sunlight. And we've got the sweat glands, which are primary role is to regulate the body temperature, the heat that builds up into the body. We've got connective tissue that provides us our elasticity and, against trauma. And then we've got the lymph blood system, which is basically an immunological response that helps to ward off and fight off infections that can occur to the body. Some of the other critical organs that we'll be talking about in the course of discussing chemical hazards are going to be the liver. The liver basically is a processing plant, if you will, of everything that goes into the body. And it's in the liver, it's going to break down or transform a material. And if it's a poison, we hope it transforms that poison from a dangerous material down to a less harmful and non-dangerous material. And there also are materials that cannot break down. And when that happens, those materials will pass on into the body, the blood system, or they can be stored into the liver and accumulate until the point of where they can start doing damage to the function of the liver. So the liver is a primary processing plant, if you will, of everything that goes into the body. Also, another processing plant are the kidneys. And the primary role of the kidneys is to remove the waste that has been generated, remove it out of the blood system, and pass it out through your urine. So just about everything that enters in through the body is going to pass and or be dealt with by the liver and the kidneys. That's why we see a lot of chemical hazards when they talk about organs that they can cause damage to, that we see they can damage both the liver and the kidneys. The central nervous system, basically that's composed of the brain, the spinal cord, and all your peripheral nerves, all the way out to the ends of your fingers and toes. That's referred to as our central nervous system. Blood is the fluid that is contained throughout the body and used to transport substances throughout the body. Hopefully those substances that are being transported are beneficial for the body. And then we have other organs like the stomach, the spleen, intestines, and our reproductive organs. And when we talk a little bit later on toxicology, we'll talk about substances that can affect some of these different body organs. So that gives us a quick overview of the anatomy of the body. The next section we're going to cover is toxicology. And as I mentioned, what we're going to do is do a basic review of toxicology. And if you've had Dr. Olson's industrial toxicology, you'll see that the material that we cover will be a review of the material that you discussed in that course. But before we go into this section, I want to take just a short break, and when we come back, we'll start on industrial toxicology.